Okay, so let's go ahead and take a look at how we can apply L'Hopital's rule to go ahead and evaluate a limit that is in this indeterminate form, 0 over 0 or infinity over infinity. Now what we want to do, of course, is we want to also go ahead and see how we did this normally. And we said that we could either factor or we can go ahead and use the conjugate. Now let's go ahead and just do a more simple example and see how we can actually evaluate limits by eliminating the factor that is making the limit indeterminate. Okay, so let's go ahead and take a look at this example here. It says the limit as x approaches 1 of x squared minus 1 over x minus 1. Now if we did a direct substitution into this particular function, then of course what we'd come up with is 0 over 0. And again, this is indeterminate. Now the thing is, of course, is being that this is 0 over 0, there's most likely going to be an x minus 1 factor in the numerator, which is causing it to be 0. And sure enough, when we go ahead and factor x squared minus 1, the x minus 1 and the x minus 1 here are the two factors which are causing this to be an indeterminate form, which is causing the indeterminate form. So we can cancel those out, and we're left with the limit as x approaches 1 of x plus 1, which is of course equal to 2. So what we can say then is that f of x is convergent to as x approaches 1. Now let's go ahead and take a look at what that function actually looks like. Here is what f of x, y equals f of x looks like. It's a straight line because it's x plus 1, but we also know that x cannot be equal to 1 here, and so therefore we have an open spot, a point of discontinuity, at a removable point of discontinuity at 1, 2. Now, let's take a look at how we can approach this using L'Hopital's rule. Notice that we come up with exactly the same indeterminate form of 0 over 0. And now, instead of looking for the factorization, which would then allow me to evaluate the limit, instead, being that I know that the indeterminate form is 0 over 0, or again, it could be infinity over infinity, I take the derivative of both the numerator and the denominator. And if I take the derivative of the numerator, it's just going to be 2x. The derivative of the denominator is just going to be 1. And now I can evaluate this limit by evaluating this limit. And so I come out with the limit as x approaches 1 of 2x, again, which is going to be equal to 2, which is consistent with the result that we have here. Okay, so that's basically how we can go ahead and apply L'Hopital's rule to go ahead and evaluate limits that have an indeterminate form of 0 over 0 or infinity over infinity. Okay, so let's kind of wrap things up. The main thing again is to remember that what we want to do is we want to be able to answer the question about convergence or divergence. That's going to be the key. After that, we need to also go ahead and take a look at limits, because limits are often going to be the one method by which we are going to be able to determine whether something is convergent or divergent. Okay? And so we said that when it came to the definition of a limit, we need to go ahead and understand conceptually and graphically how that's working out. And then algebraically, when we want to go ahead and evaluate limits, again, we want to go ahead and remember the possible outcomes and its relationship to whether or not the function is converging or diverging. And also thinking about the indeterminate form, because we cannot determine whether or not it's converging or diverging. If those indeterminate forms are in these two forms, we can use L'Hopital's rule to then hopefully be able to determine whether the function is converging or diverging. Okay, so let's just keep all of those things in mind. One last thing. Here's a question for you, because we're dealing with limits, and this is a very appropriate question. What are the three conditions for a function to be continuous at x is equal to a? And we'll go ahead and talk about that in class the next time that we meet. Okay, so hopefully that clarifies how we can go ahead and use limits to help us determine whether a function is converging or diverging to a particular value. Okay, see you next time. Bye-bye.